maybe I can try it. So, yeah, it works. Okay. And the pointer. Is this working? Here on. Yeah, it's fine. No problem.
All right. So the next speaker is Julija Zavadlav from the Technical University of Munich. Welcome.
Yes, thank you. And thank you to the organizers for inviting me. It's a pleasure to be here. So I'm going to talk about molecular modeling. So again, we're going to switch towards machine learning and machine learning force fields. So I will quickly give you a bit of the introduction, even though we heard a lot already about this. Nevertheless, so first what I will talk about, we'll talk about three aspects that are involved with machine learning potentials. So the first aspect is going to be about the impact of the training objective, which is to say just the impact of the loss that we use, so how I pose the training. And then the second story is going to be about the impact of the training data source. So we talked during the discussion about combining sources and using different sources. So here is going to be about what is the difference between using simulation data versus experimental data. And then lastly, I'll talk about Bayesian uncertainty quantification. So here, what is the impact of using Bayesian uncertainty quantification versus non-Bayesian uncertainty quantification? And this, of course, has an impact or reflects, is directly connected to active learning, which is the theme of this conference. And in general, if you see all of these three, let's say, sections have to do with how to manage with data. So they are all connected with data and the problem of having data scarcity. Okay, so to start, a short introduction that we already know. So the general motivation, why are we trying to use machine learning in molecular modeling, is this big promise or idea that, okay, if I use here, maybe it's best with a pointer. So if I use ab initio data, that I can use this data in order to train my model, and then I can develop a model with machine learning that is going to be at the same accuracy as the ab initio data, but is going to be computationally much cheaper, or almost as cheap as classical optimistic models. This is sort of not exactly true, but at least it's much cheaper than the ab initio molecular dynamics simulations. Now, this is maybe the point of the graph that it's known to you, or has most of the research in machine learning potentials is here. But actually, we try to work on another level. I mean, we work on both, but we also work on trying to use atomistic simulation data, so classical atomistic simulation data, in order to, with the same analogy, right, to develop coarse-grained models that will again have the same accuracy as the classical atomistic simulations, but will be much cheaper computationally. So when I say coarse-grained molecular models, this we usually construct by basically grouping atoms together into a bigger particles or bits, or by just removing some atoms, or in general, one could say just removing degrees of freedom. Okay, so I will mostly talk in this part. Okay, so but before let's set the scene. So how can we use machine learning to basically get us better molecular dynamic simulations? So here in this, what I call molecular machine learning augmented molecular dynamics simulations, basically use machine learning on every step, and machine learning is somehow propagating forward our simulation, right? And then we do the simulation, and we get some states from this simulation, and then we use these states basically to approximate assembly average that tells us, and from which we can compute any kind of property of observable. So there are several ways that one can do this. So this machine learning here can be different. We can pose it differently. So one way to do it is to replace the entire simulation with a machine learning model. So for example, we did this, what we call learned effective dynamics model. So here, the model is basically trying to learn implicitly the total differential equations that you would otherwise run in molecular dynamics. So the potential as well as the whole dynamic equation. And so we try to do that with a combination of autoencoders, and then in order to propagate states forward, we use recurrent neural networks here, LSTMs. And this is especially useful in the case where we don't actually know the differential equations of molecular systems. And this is true for coarse-grained modeling, where we know that if we just use the same kind of differential equations that we use in atomistic modeling, that basically we cannot reproduce the dynamical properties, right? Everything associated with time is wrong. That is because coarse-grained models are in general more smooth, so everything basically evolves faster. So every kind of time measurement that you have, you're going to measure it wrong. It's not correct. So here, with this machine learning setup, we actually learn these differential equations implicitly, and then we can actually reproduce the dynamics also of coarse-grained models. Okay, but this is just in short what we did here. The more standard approach, the one that we already heard a lot in this conference, is instead to use what is called machine learning potentials. So we are not trying to replace the entire molecular dynamics simulations, but we just want to use machine learning for one part within our differential equation, and that is potential energy. So here, the setup is that you would input to your machine learning model configurational state and chemical state of your particular material or molecule that you try to simulate. Then you use some machine learning model, and at the output you get potential energy, from which you can also compute the forces on each particles, and then this allows you to run your simulation. There are many, of course, different models here that we heard about during the workshop as well. What we use, so for the forward results that I'm going to show you, they were all done with graph neural networks, and specifically we use the DimeNet++ implementation that is also coming from Technical University of Munich. But I will not go more into the details of this architecture. And to be honest, I really don't think that the results are that much dependent on the particular architecture. If I would swap this with some other state-of-the-art graph neural network, I believe that I would get the same conclusions. Yeah, so I don't think that's so important as, let's say, the importance of data. What data, how you train it. I think that has a much bigger impact, as I will show you. Okay. And then before we go towards specific problems, I just want to mention that we never use graph neural networks on their own. We always use and combine this with what we call prior potentials, okay? So we combine our total potential with two parts. One is learnable, this in our case is graph neural network, and the other one is fixed. We predefine it and we never touch it. And so we call this prior potential. This is not a Bayesian prior potential, which is just a name that is in literature. One could also call this delta learning, right? Because we try to then learn the difference between the true and this prior fixed potential. So we notice that this is rather necessary when we do coarse machine learning potentials for coarse-grained modeling. We typically run these simulations forward in time for 100 nanoseconds to microseconds. And then, yeah, we easily notice that things can really go wrong. right? When you really try to push and you try to run these simulations for a long time, yeah, then this 1 in a billion, 1 in a million chance actually happens quite regularly, right? And so what happens typically is that, yeah, 1 in a million times you will have two particles that just so happen to be rather close together. You never in your database saw this example. Machine learning model has no idea what to do there, can easily predict attractive potential instead of repulsive. You get particle overlaps, the simulation explodes, right? So we found that just by adding some prior potential, like really helps in terms of robustness and stabilities of these models. And this is something very simple, the simplest thing you can think of, like you can build a repulsive part of a Lennard-Jones potential, let's say. And I think this is in line with what is also reported in general from the community. Right now we get a lot of papers. So this is from 2022, and yeah, papers to papers that really try to look into the robustness of these graph neural networks. And yeah, they also found that just using graph neural networks, if you run it for a long time or you're running at high temperatures, yeah, you get boom, right? So, we find that at least using this prior potential, somehow we can avoid this. Okay, so now on to our first story, and this is the impact of the training objective. So this is how you pose your loss function. Okay, so all the rest is the same architecture, same data, everything the same. So I will show you this for coarse-grained modeling. For training coarse-grained machine learning potentials, we can use what is standardly used, and this is, so to say, force matching. This is similar to what you would use when training from DFT to and train atomistic models. So the idea is quite simple, right? You match inputs to outputs, and you match this for us forces to some reference simulation data. Okay, so we only can match the forces. This is a particularity of coarse-grained modeling. Okay, but other than that, it's all equal. But in coarse-grained modeling, we know from classical coarse-grained modeling that this is not the only approach. And we can do something else. And what we can do is we can use what's called relative entropy. So instead of posing a loss like this, match these two values, we pose a loss, instead minimize this quantity, which is called relative entropy. And this is nothing but Kullback-Leibler divergence between two probability distribution functions. So here you have a probability distribution function of the states that would be generated by our reference simulation. This is for us atomistic simulation. And probability distribution function of states generated by our model. For us, this is coarse-grained model. And obviously, if you match the probability distribution function of states that you generate, you will match any kind of structural thermodynamical property. Okay? And this is the goal. So we know quite a lot theoretically from this, because this was used a lot in classical molecular modeling, but we were the first to use relative entropy in terms of machine learning potentials. And this has some differences, right? So what do we know theoretically? We know that theoretically the result that we're looking for is so-called potential of mean force. And we know that in the limit of infinite data and model capacities, these both approaches will recover the true solution. In fact, they are equivalent in this limit. Of course, you never have this limit, right? In classical modeling, we used to have a problem that the model capacity, we had two body potentials, so it was very restricted. And all the, let's say we had 10 data or 10 properties that we would want to do or reproduce with the coarse-grained model, and we could not even reproduce those. And so we had this limited model capacity. We didn't really have a problem with data. And now with machine learning, we have reverse problem. We have the problem of, okay, we have model capacities which are extremely large, right? We do 5 body, 6 body, 7 body potentials. But we have a problem of data being too scarce, right? So reverse. And just like before, in classical modeling, you would notice differences between these two approaches. Also now, due to this data issue, we notice that these two approaches are not equivalent because we don't have this infinite amount of data. and we don't get the same result. So let's look at now the results. I will show you the result on the alanine peptides that we model on a coarse grain level. So we get some data from atomistic reference simulation in explicit water. And then we want to use machine learning in order to come up with a model that is now on a coarse grain level, where we just neglect all the water, explicit water particles, we move them away, and we neglect all the hydrogens, okay? And we want this model to be as accurate as the left-hand model. Of course, it's going to be much more computationally cheaper, right? We get a computational speed up on the count that we have drastic reduction of number of particles. So here we have something like 10,000, and here we have 10. So these 2 orders of magnitude already on the number of particles, and all of these methods scale with the number of particles. And then there's another computational speed up because coarse grain models, typically because of smoother potential energy, allow for larger time step, right, that you can use. And this can be another order of magnitude speed up that you can get. Okay, so let's see how this works. So we did this and we tried force matching first, and force matching gives bad results. So what kind of results am I showing you here? So for this alanine dipeptide, we know that we can characterize this molecule quite well, or the metastable states, with 2 dihedral angles that you see here, this psi and phi. And then I can plot the density of states, how often I observe some state, on this 2D histogram that is called Ramachandran plot. And the more dark the points, the more frequent the molecule is in this state. Okay, so this is our reference from a reference atomistic simulation, and this is what we get with force matching. And as you can see, like force matching gives you another minimum here that is never in the data. You can clearly see that the minimums are the depth, right, is not correct, and so forth. And I should maybe mention at this point that here, when we do our coarse grain modeling, it's really easy for us to see how good we are doing, right? Because the reference data, we can actually also simulate it quite along. So these are like simulations from 100 nanoseconds, right? And so we can actually see this difference, right? It's very hard, let's say, can you do 100 nanoseconds with DFT, right? So you cannot even see that on a higher level. It's harder to see how wrong you are. Here we actually see it, right? Okay, so force matching doesn't really give a good result, but relative entropy does, right? And here you can see that the result is much better. And it's even clearer to see this on one-dimensional plot. So we do one-dimensional projection now to either psi or phi angle. And then you can clearly see this difference, right? So for force matching in green, you can see that it's quite off, whereas for relative entropy, with the reference, you basically here, you cannot even distinguish the difference, right? It's much better result. So in general, we can say relative entropy just gives us way more accurate result with the same amount of data. And not only that, it's more data efficient. So we did this previous results with a bit less than 1 million data samples. So we can afford this in atomistic simulations. But now if you increase the data size by 10-fold or decreases by 10-fold, relative entropy results are pretty much the same. So this is the error on those histograms that I was showing you before. Whereas force matching just is very highly dependent on the data size. Okay. And in the data set sizes that we tested, always worse. And then there's another benefit. Relative entropy actually allows us to use larger time steps that we want in a coarse grain modeling. So for relative entropy, we can use 10 times bigger time steps. And okay, these results are actually on a different system, on the system of coarse grain model of water. But just to quickly say what we get, the main result is that in relative entropy, we can actually use those higher time steps, whereas for force matching, when you go to higher time steps, you basically lose a bit on the accuracy. Yeah, so these are the positives, and you can see there are many positives. Of course, there is a negative to this side, okay? What is the negative? The negative is that the training costs more. And it costs more because in order to train the model, I need to, of course, compute the gradient with respect to my loss, and this is this guy here. And in this expression, we have this part here that requires me to obtain samples from my coarse-grained model at each iteration step. So this means I need to run simulations forward at each simulation step, and this is, of course, the expensive part. And so what we come up with is this compromise, right? We said, okay, what if we combine the both losses, right? You first maybe pre-train the model on force matching, you get semi-good result, right? And then you really nail it down with just a few iterations with relative entropy. And we found out that we can basically just use maybe 30 updates with relative entropy instead of, let's say, 300, so order of magnitude less. As a good compromise. Okay, so lastly, why is this actually better? So the reason is that data from simulations is biased, right? So here, when we get reference data, we just basically run the simulation and we subsample and just get every 100 snapshot, we take it as a data set, right? Of course, simulations are done and some statistical assembly. For us, this is Boltzmann distribution, right? And so this data is not, has some distribution. So it's in this way biased, right? And so this means that when we sample this, so this is a sketch, what happens is that basically, let's say that we would have a double well potential, like one-dimensional. Then from Boltzmann distribution, we would basically sample mostly states in these two minimums, right? And very rarely the transitions in between. So what happens is that from just these points, the force matching has very hard time distinguishing between the depths of these two wells. Just because here, let's say that there are two plots of two potentials, they have always the same gradient of the potential, so forces are always the same. And so on the left-hand side and on the right-hand side, whereas in between you don't have data points, or you have very low amount of data points, and so you cannot capture this difference here. And the second thing is that for force matching, the data perceived is basically noisy data, because in coarse graining, we lose some degrees of freedom, right? So if you think of this example that I showed here of two molecules, then if I rotate one, I would always get different forces, but on a coarse grain level, this is always the same. So for the same input, I get several different outputs, and the task of the machine learning is then to find the mean, right? And then in relative entropy, because we are running these forward simulations during training, we also manage to correct for all the integration errors that we have always in the simulation, right? Because of the numerical integration. Okay, so this kind of concludes the first story, and now I want to move a bit to the second story, which is the impact of training data source. So obviously, when you use training data from simulations, every simulation has a limited accuracy. So if you are using classical microdynamics, then we know that this is sensitive to also employed force field, and it's not really accurate, right? And also if you would go to ab initio method like DFT, then you have sensitivity to functionals, and also DFT does not always match the experiment, right? Furthermore, if you then want to really do, I don't know, copper cluster kind of simulations, then it would be so expensive that is, let's say, then you cannot really afford to do much, or you can only do small system sizes. So what this in the end translates is that you did all your work, you used as much data as you could, you trained your model, you did the fanciest model out there, but you were training to wrong answer, and then machine learning model will also give you a wrong answer, right? So it's not guaranteed that you will in the end match the experimental observations, right? So what can we do about this? Well, I mean, it's quite, or maybe to give you a concrete example of this, in particular from machine learning potentials, we looked at the example of titanium, and we trained this model on a DFT database that we took from a reference publication. So we reused the data. So this was trained on the DFT data with energies, forces, and virial, as you would standardly. We get the numbers are not really now important, but we get, let's say, reasonable result compared to the previous publication. And then you use this model and you test it on mechanical properties. So these are different elastic constants, let's say, of the stress tensor. And versus temperature, and you try to compare that with experimental results. And it's the exact points doesn't matter, right? But you can clearly see that there is a strong deviation from experiments to whatever your machine learning model predicts, right? And this is basically also similar to what was previously reported. So there's this huge discrepancy. And if you would now compare like your machine learning model or machine learning potential with the classical potentials, you would get that in this particular property of mechanical properties, classical models are just as good. So, you know, what's the point? But we can fix it, right? It's not a loss. How can we fix it? We can use this, right? The things that we do know from experiments, we can use it in the data. Okay, but it is a bit more complicated to do that training, right? So when my training data is from experiments, then it's more complicated because experiments will not tell me the energies and the forces on the molecules, right? What I can measure experimentally is the properties of some observables, okay? And I pose the loss as matching my observable that I measure experimentally with the one that I measure in a simulation. And then in order to train the model, I need to compute this gradient of the loss with respect to parameters, right? And now it becomes a problem because this gradient, this loss, does not explicitly contain explicit dependence on the parameters of the model that I try to optimize, right? If we think about it, let's suppose that some property just depends on the last configuration that I see in the simulation. Then when I would like equation that is basically L2 norm between these two, then I have this result that depends on the last configuration. The last configuration depends on my model that depends on the parameters, but also on the last previous state. And then this state depends on the model, but also on the previous state, and so on and so on and so on, right? We have the dependency all the way back to the initial start of the simulation. So what this means is that if you want to compute this in general, you basically have to do the back propagation to the entire molecular dynamics simulations. Okay, so through all the operations of MD, you need to back propagate. Obviously, this is very computationally costly, but doable. Okay, so we have now totally end-to-end differentiable molecular dynamics code, nicely provided by Google. It's called JAX MD, and you can do this theoretically. But in practice, you would face many obstacles, right? The first one is that this is huge memory intensive because you need to, for back propagation, right? Remember, you save all the states in the forward pass in order to use them on a backward pass. And you think about this is MD simulation, all the operations, right? This is huge memory intensive, which means that we did some like simple tests. So like a 2000 ideal gas particles in one-dimensional external potential, toy example. And this external potential is modeled with a neural network with some approximately rough parameters that we would have in neural network potentials. And we saw memory overflow with the classical GPU above time steps that go above 1000 time steps. For atomistic models, this would be 1 picosecond. Now you tell me, 2 more minutes? Okay, I will try to make it fast. So yeah, basically you cannot really measure many like properties in a time step of 1 picosecond. And the next problem is that these methods are prone to explosive gradients. Again, when you increase the simulation length, basically this magnitude of the gradients explode. You cannot use this in training. So what we come up with this alternative approach, that basically what we do is we use what is already known from statistical physics And we use perturbation theory from Zwanzig from 50 years ago in order to come up with a different route how to get this gradient without having to go through the simulation. And now this means that we are, of course, much faster in computing the gradient. We don't have memory issues, we don't have exploding gradient issues. And or in summary, we can actually do like real kind of systems, right? So we tried this on a coarse-grained model of water. Maybe I skip this one and I show you the next example. So we also did this for atomistic model of diamond. So here, for example, we used, we tried to actually reproduce these mechanical properties here, for example, for diamond, right? And we are training on models that are not toy models anymore. So here, this is the actual model that setup or system that we used in training. So this already contains thousands of atoms and it's a dense system, right? So you can actually do something with this because the previous approaches were, let's say, only for 10 atoms going around, right? Toy examples. Okay, so you can see that we can actually match now these experimental properties. Of course, the experimental data is also very limited, right? And that means that if we don't use enough data points, then our solution is under constraint, and this is what we saw here. And so when we plotted phonon density of states, each time you train a model, so these are 10 models randomly initiated, you always get this different solution, right? And so we see as a possible solution to combine basically DFT and experimental data, and this is what we are doing now. So we try to iteratively do like one iteration on DFT, one iteration on experimental data in order to be in match experimental observations, but also constrain our model to some result, right? Okay, so I'm not sure if I have a lot of time with Bayesian uncertainty verification, but actually, maybe just I say something briefly. So we are looking into how to get accurate uncertainty quantification, right? And this is, of course, connected a lot with active learning, where this is explicitly needed. But also, I mean, in the end, we are doing simulations. We want to know how well or how reliable our predictions are. So in terms of active learning, and if we do active learning on simulation data, then we want uncertainty quantification on potential energy, which is, this is direct output of my machine learning model. So it's the most trivial thing, or from all of the things that I will say, the easiest thing to do. Forces, the uncertainty of the forces are a bit more complicated, right? Because forces are now gradients. But then if I want to do active learning on experimental data, then I would like to have uncertainty quantification on the observables. And this is the most complicated, right? Because I have to translate somehow the uncertainty of the parameters of this model through my whole simulation to get uncertainty here. But this uncertainty is actually the most important one when we try to assess how reliable simulations are. So we try to do Bayesian methods, as they are believed to be the best. And of course, we cannot really do Bayesian methods like in Markov chain Monte Carlo, right? Because they're too expensive when we have huge data sets and very complex models. So what we do is like this big data trick is that we don't kind of like in gradient descent to stochastic gradient descent, where you do the switch from computing the gradient on the whole data set to some batch, right? We try to do the same here in Markov chain Monte Carlo kind of methods. The likelihood we are not computing it on the full data set, but on a mini batch, okay? And so this is the trick behind it. We tried this for the first time for machine learning potentials. And it was very surprising to us that we found out that actually these Bayesian methods are not also so like can be, the results can be good, but can also not be good. Okay, so the most important thing is to use multiple chains, because in single chains you get very bad results that are certainly not correct. This is also true for for this Hamiltonian Monte Carlo methods, which are considered to be gold standard Bayesian methods. And we actually, when compared to non-Bayesian methods, like ensemble methods, we actually don't see that much improvement. But of course, we are computationally, Bayesian methods are always more costly. Right? So this may be the main message. We also tried this. So this is, let's say, uncertainty on the potential, so the direct output of my machine learning. But we also can do uncertainty on the properties. So this is, for example, for a model of water, and the property here is the structural property, or like angular distribution function, and we can test this, let's say, when the temperature is the same as our reference data, and where we get small uncertainty, obviously, because we trained here. And when we go to some other temperatures, we expect higher uncertainty, and this we can actually obtain from these models. But again, much to our surprise, we are not doing much better job than the standard assembly method. Okay, I will just a take-home message. So yeah, I think in general, the problem is in the data, and we try to overcome these data issues by just proposing better training objectives, like with relative entropy, try to combine data sources, and as well as we try to use active learning, of course, and or combination to having good uncertainty quantification. Thank you for your attention, and I'm happy to answer any questions.
Thank you very much. Questions? Yes.
Thank you for your very nice talk. I have several questions, and the first is about the force match. From my point of view, why your method is better? Why coarse-grain is better than force matching? It's because in your prior model, I think maybe you consider the non-local effect is considered, and from my point of view, the way you deal with the molecules will introduce negative charge into the system, and that will cause some non-local effect, and maybe not good to be captured by DAMNet. And I do think you said that if you use other models, then these results may still be the same. But maybe if you consider some models that incorporate with this non-local effect, I think force matching may also be good. This is first question. And for second question is about the uncertainty quantification, about the Bayesian part. Did you consider another way, like use stochastic variational inference for mini batch gradient descent? Descent. That could be also a good choice to get uncertainty for mini batch.
Okay, maybe I answered the second question first. We didn't consider it here. Yes, it would also be, I agree, it would be a good choice. I mean, there are many methods, right? We cannot test everything. And regarding the first, I'm not sure if I understand the question. What do you mean by local effects?
It's because because you removed all the hydrogens in the molecule, right?
Yes, I remove.
So I think that could introduce negative charge into the system. This is difficult to be captured by maybe DAMNet, but it can be dealt with some other model like SpookyNet or something new. That can consider the non-local effect.
So this has nothing to do with the way we do it. The removing hydrogens is not a problem. We are not explicitly doing with charges, right? So this is all done within the network, right? Basically, you can think of it not as removing the charges, but as, if you want, you can also think of it like this. Maybe I didn't say it correctly, But basically, you can think of it as grouping this CH3 group into one particles. And this is, it's not technically removing, but maybe putting this into one particle. So this is a more correct way of what we are doing. So this is one thing, and I really believe that you would get the same thing with different models. So the same molecule was also tested with force matching, or the results are out there for a similar kind of coarse-grained model. There are some variations, and they actually get same kind of result, and it's a different graph neural network. So that's why I can pretty confidently claim that it's not about the architecture. Yeah, and we also did try different kind of variations here in the coarse-grained model, and we always get the same kind of message. So I really don't think it's an architecture, but I cannot prove it.
It was great to see that you can combine the machine learned force fields now with experimental data too. And I was wondering if the same framework can be used to train also on higher level computational data. Couple cluster you mentioned as one example, where you don't have experimental data maybe for a system, or if you wanted to check against experimental data and you wanted to use a very high level method, or are there better ways to incorporate, say, couple cluster data into a force field than your approach?
Okay, so what I saw out there is basically a couple cluster. You can only get a few samples, right? But what you can do is you can train the model first on a DFT database and then transfer learn to couple cluster. I think this is a standard thing out there. In terms of our approaches, well, for us, it doesn't really matter where the data is coming from. We call this reference simulation. So you can, the framework doesn't really care.
So would it be then, I don't know if you've tried it, would your approach be more efficient maybe than the conventional approach in getting the same level of accuracy?
You mean with this relative entropy?
Relative entropy and then the back propagation to get to the higher level of fidelity, not experiment in this case, but then higher level theory as reference data.
Okay, so if you don't use if you use higher level theory, then you have access to forces, potential energy, then you don't really need this back propagation to simulation. There's no need for that. And in terms of relative entropy, so one could think of what can we do about relative entropy and use it in terms of ab initio data in general. But just let me get to one slide here. In order to do these updates, you see that we have here samples from your reference simulation, and this is a like an assembly average. So so when we do this for coarse-grained models, we can get from reference simulation, and I showed you it was a bit less than 1 billion data points for one molecule. So it's like a statistical assembly, right? So if you give me just 1,000 samples per molecule, I'm not sure if this is going to be statistically accurate. So I think it would be a bit of a problem, but yeah, one could try and see. You never know where these limits are, right?
Thank you. Let's thank Julija once more.